Perimeter. In this lesson, we will learn to calculate the perimeter of compound figures containing sectors or sectors of circles. Also, we will learn to solve problems related to the perimeter of compound figures containing sectors or sectors of circles. During our lesson, we may see examples like this. This is a Neumann window. As you see here, in the Neumann window, the half a circle or semicircle is attached to a rectangle base. So this is a compound figure containing a sector or sector of a circle. And in this diagram, so if we have to find the perimeter of the shaded area, you can see that this figure contains two sectors. And the last diagram, you can see here the four semicircles. The four semicircles are attached to a square of 14 centimeters. It has four sectors. So it's a compound figure containing sectors of circles. So as a prerequisite, the things that we're supposed to know from the 9th grade class. So I assume that you know how to find, what do you mean by the perimeter of a rectangle and perimeter of a triangle or perimeter of a circle, or which is actually called circumference of a circle. So we know the perimeter of a rectangle of length L and breadth B is given by 2L plus 2B, because the perimeter means length around the figure. So we have two sides of length L and two sides of breadth B. That's what we get, 2L plus 2B. And the perimeter of a triangle of side ABC is simply A plus B plus C, the length of three sides. And the perimeter of a circle, or we call it the circumference, is given by 2 phi r. R is the radius, and the 2 phi is the angle at the center, angle around the center, or angle at the center over here. So which is in degree, we know it is equal to 360 degrees. So which is same as in radian, it is equal to 2 phi radian. So that's what we get this formula, 2 phi r. Sector of a circle and arc length. Right now, we need to figure out how to find the length of a curved part of a compound figure. So the curved part is coming from a sector of a circle. So here is a sector of a circle. It's a part of a circle enclosed by two radii and the intercepted arc. Now, in the sector, this is the center, and this angle over here, we call it angle at the center. And these are the two radii. These are the two radii. And this is the arc. So here is a sector, and this is the arc. We are interested in the length of this arc, so we use the symbol L. So we want to figure out a formula for that. Now, what you see over here is a sector. Again, this is a center, and the distance from the center to any part of the circumference is called the radius. And here is the angle at the center. The important word right now is angle at the center. Angle at center. If I go around this center, that called angle around center. Angle around the center. So angle around the center is always 360 degrees. So what you see over here is that the larger the angle at the center, the longer the arc length is going to be. the longer the arc length is going to be. That means what? The arc length is going to be directly proportional to the angle at the center. So what we got over here is that the arc length is going to be directly proportional to the angle at the center. Angle at center. Now let's complete this table, and at the end we'll be able to figure out the exact relationship between the arc length and angle at the center. So the first one what we have is a semicircle, right? And here we want to find what? Angle at the center. Clearly the angle at the center of the semicircle is equal to 180 degrees because it's a straight angle. And then we need to find angle at the center as a fraction of angle around the center. So angle around the center is always 360 degrees. And then arc length as a fraction of the circumference. Clearly you can see this arc length on this semicircle is actually 1/2 of the arc length or the circumference of the circle. The angle at the center of this sector is clearly 180 degrees. So the angle at the center as a fraction of angle around the center. So we get 180 over angle around is always 360. So 180 over 360, which is equal to 1/2. Now the arc length as a fraction of the circumference. Clearly we know the arc length of this semicircle or half a circle is clearly 1/2 of the circumference. So therefore the arc length is equal to 1/2 of times 2 pi r. 1/2 times 2 pi r. So in this sector we see here the angle at the center is equal to 90 degree, and clearly you can see the arc length as a fraction of the circumference is, which is actually 1/4. 90 degree. So 90 over 360, which is 1/4, and in the figure you can clearly see that the arc length is actually equal to 1/4 of the circumference. Therefore we get over here arc length is 1/4 times 2 pi r. Now in this one you can see angle at the center is 45 degrees. So angle at the center over angle around the center 360 is clearly 145 over 360, which is equal to 1/8. Now if you look at the figure, now clearly the arc length is equal to 1/8 of the circumference. As you see here, we can fit two sectors like this in 1/4. So the 2 times 4, which is 8. So we get 1/8 over here, and therefore the arc length is 1/8 times 2 pi r. Now if I have a general angle, so angle at the center is a theta in degrees. Therefore angle at the center as a fraction of angle around the center is theta over 360. Now if you carefully look at these two columns, what we see is they are going to be equal. Angle at the center as a fraction of the angle around the center is same as arc length as a fraction of the circumference. So 1/2 is equal to 1/2, 1/4 is equal to 1/4, 1/8 equal to 1/8. Therefore arc length as a fraction of the circumference for this one has to be theta over 360 degrees, and that will give you the arc length theta over 360 times 2 pi r. Now we have figured out exact relationship between arc length and angle at the center. It actually is same as arc length over circumference is same as angle at the center over angle around the center. So the arc length is L, and the circumference of the circle, we know it is equal to 2 pi r. Angle at the center is theta, and angle around the center is always 360 degrees. So if you multiply both sides by 2 pi r, clearly 2 pi r cancel out, so we get arc length L is theta over 360 times 2 pi r. So in this example, we want to find the arc length of a sector, the arc length of in this problem, and we are given angle at the center is 120 and the radius is 10.5. And let's write down the formula first. So the arc length is given by theta over 360 times 2 pi r. Now if I substitute the values, so we have theta equal to 120, and we're going to use 22 over 7 for phi, and the radius is given as 10.5. 120 is a factor of 360, so that gives us 3 over here. And if you see 2 times 10.5, which is 21, so 2 times 10.1, 21, cancel with 7 times 3. So what we have is L equal to 22 times 3 in the numerator, divided by 3. 3 cancel out, so we get L equal to 22 centimeters. And in the next example, we are given the arc length L is given as 22 centimeters, and we want to find angle at the center. So let's write down the formula. Again, the arc length formula L is theta over 360 times 2 pi r. Now if I substitute values of L and R, then I'll be able to find theta. So L is 22, theta we want to find, phi, again we use 22 over 7, and R is 14 centimeters. You can divide both sides by 22 clearly, so you get 1 over here, and the 7 cancel like 14, 7 times 2. Also this 2 cancel out, 2 is a factor of the 360, which is 180. So we have 1 in the left hand side, and the right hand side we have 2 theta over 180. Clearly again 2 is a factor, you get a 90. So we have 1 equal to theta over 90. Now multiply both sides by 90. So this 90 cancel out. Clearly we get theta equal to 90 degrees.